I'm very pleased and proud to introduce our speaker today. And I want to make a few comments before I pass on the control to her. Now, when I was looking at her CV and also the summary that she gave to all of us, one thing struck me, and that was very important. Between 1971 through 1981, it was a momentous time for her. She was very, very productive. 1971, she got her degree, her BA. At the same time, she got her first child. And then in the following 9 years, she did even much better. She got 4 more kids and 2 more degrees. So I consider 1971 to 1980 as one of her most productive periods. And then 1981, of course, she came here to Goddard, and some of you know Anne has not left this place since that time. So let's give her a loud of applause because of doing an excellent job, being very productive in 1970s through 1981, and also being here for that one. Let's give her a loud of applause to all her students. Well, she has been here. She has been a deputy project scientist for UARS, Upper Atmospheric Research Satellite. And also she lasted for about 14, 15 years, and then she transitioned on to Oregon as a project scientist from 1998 through 2010. Then 2010, when Mark Schober left, they had no one else to pick, and they went all the way to Ann Douglas. So let's give her a clap for doing a good job once again. Let's give her a round of applause. Now her titles, and she's very proud of this. She always liked to identify herself as a mother. That's number 1. She is a mother. And number 2, she is also a grandmother. And above all, she is also a scientist. So the 3 roles are very difficult to combine. And today, she's actually going to show us, to tell us how she has been able to juggle those 3, being a mother, being a grandmother, and also being a superstar scientist. So please help me welcome Ann Douglas.
Well, that was an amazing introduction. Okay, so I was thinking about how I would start this talk, and I thought I would start out with my credentials, some of which you just heard. And apart from the satellite projects, I'm a co-lead for the Goddard Earth Observing System Chemistry and Climate Model. And I've written a lot of papers, and I was lucky to be elected a fellow of the AMS and the AGU. But you also see on the right-hand side that my personal credential list actually is longer. I've been married forever. I have 5 kids. The last one actually was born in '83, so she wasn't in that big productive decade. We consider her the caboose. They're all married and they're all taxpayers, which makes me a complete success. And if you look at their jobs, you see I have one in business who's the IT lead for a company, and a chemist and an emergency room doctor. And I also have a social worker, and she's fabulous. But I have an oceanographer, so I've actually totally reproduced because I have my own earth scientist. And not many people can say that. We were the first mother-daughter in the AGU. And I have a lot of grandchildren, including our miraculous quadruplets. And I could talk about them for a really long time. But I won't. And I'm a regular person. I used to tell people all the time I was just a regular person. Since then, I have embraced my nerdiness and the fact that I do think about things differently from other people. Now, I made a timeline because I think you can't really escape the soup that you're born in. And a lot of things were happening during my life. I have marked when my kids came and when I got my degrees. But you can also see there were a lot of events from Sputnik, living through the 60s, civil rights, the Vietnam War, assassinations, all kinds of things going on. And I wanted to highlight just a couple of things. Sputnik, the Silent Spring, the feminine mystique, a big decision I made in 1975, and then finally getting my PhD in 1980. Sputnik, what did that do for us? Well, we had the new math. It was great. Everyone wanted us, my generation, to learn math and to learn science and catch up with the Russians. That's what it was all about after that. So there was chem study. Anybody besides me observe a burning candle their first day of chemistry class? That was short-lived. But there's a lot of energy for high school students with scientific leanings. And my dad, who was not particularly a supporter of women in education or women doing anything, did constantly tell me if I learned to do math, I could do just about anything. Silent Spring in 1962, people did start to talk about the environmental movement, and I was not immune to that. I was listening to that myself. 1963, The Feminine Mystique was published. I did not read The Feminine Mystique in 1963, but it certainly affected the choices and the way things were going as I was being raised. I'm sort of a child of both generations. My brother was raised with privileges, better education, expectations. My sister and I had to make his bed. That's true. My sister and I, though, we were raised with none of these things, but we also had a gift, and that was that there were no expectations. So if you're raised with no expectations, you don't have to do much to exceed expectations. So I've always felt like I was doing more than I was expected, so that's great. And then it is also really important that when I was graduating high school, my mother was hell-bent on her daughters getting a good education, and she took a full-time job to make that happen. And that had a big impact on me because I felt like I couldn't let my mother down when she had gone to so much work for me. And then I went to Trinity, which is now Trinity University here in Washington, D.C., where I had women professors in math and physics who were raising families, and they were relentlessly pushing me towards graduate school. And this is really a big thing because at that point, neither my mother nor father went beyond high school. My father was the only one in his family to graduate high school. Everyone else had to drop out and go to work when they were still 10 or 12 years old. He was the youngest. So to me, someone with a PhD was like a god or a goddess. I had no concept that I could do that myself. But they were relentless, my teachers. So fast forward a little bit, 1975, I was very idealistic. We had moved to Iowa for my husband's job, and I was now going to go to Iowa State. I hadn't chosen the physics department for anything they were doing there that I wanted to do. I didn't know what I wanted to do. I lived 40 miles away. I had to give up lab work. I was expecting baby number 3. I was the only woman graduate student in the physics department, and I was searching for a new research area, and I thought I would love solid state, and I just hated it. Just totally hated it. And I couldn't imagine like subjecting my brain to it for one more minute than I was forced to. So I met John Stanford, who was a professor there, and he was just a really wonderful man. He was very smart and open to all kinds of things, like that I could go to graduate school part-time. Didn't bug him that I was pregnant, and he was just very positive and very supportive, and I thought, this is where I need to be. So I chose to do something for the environment. I joined John Stanford's research group and started looking at satellite data. And you know other famous people are John Stanford students: Paul Newman, Leslie Late, Jerry Zemke, Mark Olson. Other famous people who were John Stanford students in other institutions, Bill Randall, Gloria Manny. So we have this strong Iowa State bond. Okay, I graduated, and honestly I had no plan beyond that. What should I do next? My first goal had been to teach in a small liberal arts college because that's where I came from. And I thought that physics and environmental science would make me like a #1 candidate. In reality, there are hundreds of applications for every job. And when your cover letter says 4 children and I'm looking for a 3/4 time position, people do tend to throw it in the trash. In fact, I have met people who told me they threw it in the trash. So, c'est la vie. It's a 2-body problem because my husband was a chemist and we were looking for 2 jobs for both of us. And Washington, D.C. looked like a great location, and John Stanford was here on faculty improvement leave. I did spend a year being in charge of Paul Newman, and that could be a talk in itself, but it's not.
He's out of school.
And I had the good fortune when I got here to work with many talented people. It's the same branch I've been in the whole time. John Frederick first, and then Rich Stolarski. And Rich taught me just about everything I know about chemistry. They were very supportive. I didn't work full-time till 1989 when my youngest started kindergarten and oldest started college. And also, one of the reasons that I stayed here, people knew I would never leave as long as I had a child in the child care center. I mean, the child care center is primo, and it worked very well for me. But I was also here at a really great and fortunate time. So this is another timeline that tells you about some of the things that were happening here at NASA during this time period. So first we had Nimbus 7 and we had LIMS. We launched URs in 1991 and then Aura in 2004. So there were tons and tons. It's the information age, so much data. It's just wonderful. But also many, many other things were happening. The ozone hole was discovered in 1985. You had the Montreal Protocol shortly thereafter. So you had an opportunity to really be involved in a field as it was evolving and as that was developing. So we started out, I was a 1D modeler, a 2D modeler, and a 3D modeler. I don't think there's very many people who can say that. But the advantage of that is that you really get to know what's inside the model because you're there while it's being developed. And you're helping develop it, of course. I've also got on the bottom that we have aircraft assessments about every 20 years without closing the problem. So I don't think that's a solved issue yet. And now we've moved into the era where we're looking at chemistry and climate with some really high-level models. So, approach to this talk, how to come up with an approach for a talk like this. Well, so far you've seen some history. Back in the day, back in the 90s, people were very interested in Myers-Briggs, and I took the test and found out I was an ENFP, which is extroversion, intuition, feeling, and perception, 2 to 8% of the population. And these are the characteristics of people who do this. They say, giving life an extra squeeze. You're people-oriented. You're very optimistic. I felt like these were very true with me. More starts than finishes, also true, maybe sadly. And so I spent a lot of time thinking how I'm going to talk about this talk. So I'm going to tell you my rejected ideas. So my first rejected idea was how raising a family is perfect preparation for running a science team. Because sometimes you have to share bad news. And when you have bad news, you would be surprised at how people react. They whine. And I just couldn't tolerate it at all. I would send them to their room. I'm not talking about it. You know, like, we can do decisions, we can make strategies, we can do a lot of things. There will be no whining. And that's really useful because other people are affected by it. It makes them nervous or something. And I'm just like, no, we're not doing that. But that's all I'm going to say about that. I can be influenced, just not by whining. Rejected idea number 2 was this work-life balance. 39 years on a teeter board? No, you don't really want to hear about that. People might ask me, how did you do this? And I mean, really, honestly, I don't know. Days have 24 hours. I was pretty busy all the time, but my days aren't longer than yours, so whatever I could fit into that time, I fit in, and what I couldn't fit in didn't happen. And somehow we made it out. If I was going to give someone any advice, I would say don't just focus on small children because it doesn't stop. The mother gig seems to continue. You get through soccer practice and scouts, you have teenagers with the challenges that they present, and then your grown-up children can surprise you with accidents and illnesses and all kinds of other things. And then one of your daughters might even have quadruplets. And when that happens, you know, all kinds of things change for you, and you just have to learn how to go with the flow, I guess. There's a book that I have essays in, this motherhood book, and my daughters do too, and it was about work-life balance, where I wrote about what I thought balancing meant, and they wrote as subjects, like the balancees, how it had been for them. And so it's kind of interesting to read what they had to say. Okay, now rejected idea number 3 is getting into satellites. There's a big fascination with satellite images, and when you're a project scientist, when people want to know what's going on with your satellite, they want one picture, one paragraph. They want a result that they can look at right away. And I think that's great. And I love this image because this was from the early part of Aura, and it showed the SO2 over China and the SO2 over the United States in the Ohio Valley. And it showed that we really don't have a lot of SO2. And the Clean Air Act is buying us something. And I feel like the whole world needs to see this image. But at the same time, it's not really quantitative, and its value is limited in a scientific sense, while in public relations, maybe it's really important. And so I want to emphasize that satellite data, you have to get beyond the image, and for it to be really useful, it has to be useful in a quantitative sense. This is a picture that shows what I mean by that, where this is the SO2 retrieved by OMI between the 2005 and 7 on the top, and then 2008 and 10 on the bottom. And you can see that it went down when you look at it, but if you do the quantitative work, you can show that it went down in an amount that's consistent with what is reported by the industry for what they say their emissions are. And so that's really great. You've got a validation of your ability to calculate what the emissions are, and the implication is that we can use this data to get emissions for other parts of the world where we don't have such good reporting. But this is really all I'm going to say about that. Just that satellite data really needs to move beyond the picture and into being quantitative use, and I think we've been seeing that happen more and more over the last 20 years. So what I decided to stick with finally was to talk about the interplay among observations, not just satellites, but aircraft, ground-based, and satellite, and what I would call the conceptual model and its implementation. Most people do not distinguish when they talk about modeling a conceptual model from the computer code, but they really are two very different things. And if you have a well-developed conceptual model, it can help you to understand what's happening in your numerically discretized solution to the equations on a finite grid. Not always the same thing. So when I got here, there was a strong conceptual model for ozone. And you would see pictures like this, that we needed a fully coupled model because ozone was related through related photochemistry, dynamics and transport, and radiation. And that was known for a really long time, and you would see a lot of pictures that had this kind of diagram, but quantitatively we weren't able to produce that model in the 1980s. We had limitations, our knowledge and computing, so it was impractical to think you were going to code up the fully representative three-dimensional model with fully interactive ozone. The photochemical data was still evolving that you need as input to the model. Major processes were completely unknown at that point. And then there were other things, just like I would call features of the circulation, that were unknown. But we did have some data. We had Nimbus 7 LIMS, we had TOMS, we had SAGE. We were learning a lot, and we had no choice, really, but to use the data that we had to really develop the conceptual model. One of the things that you learn about a lot in ozone is that there's a number of loss processes. O plus O3 is the first one, where oxygen atoms react with ozone. But you also have catalytic cycles involving hydrogen, nitrogen, and chlorine radicals. These are temperature-dependent loss processes, and they go in order. This one is the most temperature-dependent. Oh, I should have put NOx, then HOX, then chlorine. Chlorine is the least temperature-dependent. And so ozone will respond to a temperature perturbation. People spent a lot of time thinking about this back in the 80s. So you had an unknown future because there wasn't a Montreal Protocol yet, so you didn't know how big the CFCs were going to grow. At this point, we expected ozone destruction in the upper atmosphere. We didn't know about a lot of things. We use principal ozone loss processes in their expressions using rate-limiting steps. That's what I want to focus on right here. So this is an example. This is the chlorine cycle for destroying ozone. You have ClO plus O reacting, giving you Cl plus O2, and then the Cl reacts with ozone, reacting to give you ClO plus O2. So the net of this is O plus O3, giving you two O2s, and the top one is what's called the rate-limiting step. Well, I thought about that for a long time, and I realized that the best way to think of it was just kind of like doing the wash and getting it into the dryer, because I had 5 kids, I had a lot of laundry, and you can only do it so fast. You know, if you have a pile of laundry this high, which is no exaggeration, it has to go through the washer. You can usually do 2 loads in the washer for 1 load in the dryer. So the dryer is totally the rate-limiting step. So this is all part of building the conceptual model. We took our one-dimensional model and we did a Monte Carlo analysis of reaction rate uncertainty and computed the sensitivity of ozone to chlorine. and showed that it's related to the computed present. So using the uncertainty in the reaction rates, everything else the same, you could get CLO values at 25 kilometers that would vary from well, more than a factor of 2. And the same with nitrogen oxide. These are very huge ranges. But then if you looked, and you could get very big changes in the ozone column. But then if you looked at the data and what you actually had for CLO, it was telling you that these really large values and these really large changes were very unlikely. And this is where we were with the conceptual model in 1985 when the ozone hole was discovered. And then everything changes. Lots more work on this conceptual model. There were aircraft campaigns that gave us a lot of details about how the chemistry worked. There was laboratory work that backed up what was being learned in the aircraft campaigns. And we had to make these major additions. You had heterogeneous reactions on polar stratospheric clouds, and you had a new cycle for ozone loss that didn't require UV light. These were huge changes to what we had been modeling and using to predict before. So that really shows you how you have to have the data. You have no way of knowing whether your conceptual model is complete until you have the data. So during the 80s, we started getting all this data that challenged the conceptual model and showed us ways we needed to expand it. Developing a role for background sulfate aerosols. I can remember papers that said that the background sulfate layer was curious but had no impact on atmospheric chemistry. And of course, we know now that's absolutely false. And we also learned a lot about the way the dynamics worked in the stratosphere, and I'm just emphasizing here the polar vortex and its isolation, descent of air from the mesosphere, and other features that were necessary to have the ozone hole exist. Now, the way that the satellite data interacted with the model, for example, this is an example that would illustrate that. You had an ozone annual cycle that you could derive from measurements, and that's what the top 2 lines are here. And then you could compare that with the ozone annual cycle you were deriving with a 2D model. Now, it had specified dynamics and temperature, so you knew the temperature was right. But if you just used the chemistry that was accepted in the day, you got this very, very low amplitude. It's about 1/3 the observed amplitude for the seasonal cycle. So what you're finding there is that modeled ozone was simply not as sensitive to temperature as observed. And you had to try and understand why within the context of your photochemical mechanism that you were using. Well, clearly, again, the O plus O3 is most temperature dependent. The O plus CLO is the least temperature dependent. Chlorine had too much influence, and that's pulling down the annual cycle. So the lab experiments of the time did not rule out but could not confirm that when CLO reacted with OH, it made HCl. But if you tested the sensitivity to that, you started to get an amplitude for the annual cycle that rose because there was a lesser role for CLO. And then this was ultimately determined, measured in the lab to show that this reaction, CLO plus OH, produced HCl about 7% of the time, with a big change in the sensitivity of upper stratospheric ozone to chlorine. Now we had 2-dimensional models, and you could begin to use the measurements of long-lived tracers like nitrous oxide or methane side by side with the observations. And even then, this is 1989, we had sufficient data that you could select a better simulation by making a side-by-side comparison, changing only one aspect of the model. In this case, it was the circulation. And we also found that our global ozone change was sensitive to what the circulation looked like. So this is laying the groundwork for understanding how the more complex models respond when you increase chlorine. This result is limited in terms of the numbers because it's old photochemical input. There have been some pretty big changes between 1980s and the 90s, and there were also no polar processes and there were no aerosols. So the model that we were using here was still lacking some important physical processes. So when you get to about 1990, you still wanted to do this 3D model where you could do the whole thing, right? That was the goal the whole time. It's actually great. When I came here, we wanted to have a 3D model that was fully coupled with chemistry, and maybe 5 years ago is when we got one. It's so exciting to have been here, from the just desire to the fulfillment. But in 1990, if you wanted to have a three-dimensional model with chemistry, you had positive and negatives to it. A positive would be that you could make a realistic representation of polar vortices that you would need for polar ozone chemistry. You can't do that in 2 dimensions. And you would have actual advection rather than zonal mean advection and diffusion. During the 90s, people spent a lot of time talking about chemical eddies and whether it would matter whether something went straight towards the pole or whether it took a meandering path, and how you could quantify that in a lower dimensional model. The negative of trying to couple a 3-dimensional model with chemistry, apart from the fact that we really didn't have the computer power, would be temperature biases that affected photochemistry enough to make it behave differently with the computed temperatures than it would actually behave. And outside of those biases, the polar vortices were too cold and they were too stable, and you couldn't simulate ozone hole breakup realistically. So we came up with a solution. It's a temporary solution. Or maybe it was a Band-Aid, because we had a lot of issues with it even while we were calling it a solution, which was the 3D chemistry and transport model, where you give it input, perfect meteorology, which you get courtesy of the assimilation people, and then any difference between your observed and model constituent evolution is going to be due to photochemical deficiencies. Well, that was the theory. Of course, we spent many, many years worrying about the transport that you got from the assimilation systems that were available at that time. And again, that's another problem that's been largely solved over the course of my career. But we tried to put this into practice, and one of the things that we were learning about then was from the aircraft measurements, was that long-lived constituents were correlated with one another. So this is from an aircraft flight. This is total reactive nitrogen, NOI, which is very conserved in the lower stratosphere. Whoops, this one's ozone, I'm sorry, and the bottom layer is NOI. But if you plot them one against the other, you get something that looks a lot like a straight line. So you would look at that in your model and you go, okay, can the model do this? Well, no, the model couldn't do it at all. And it wasn't because we didn't have the right concepts. It was because we had terrible numerics. And I think that's one of the reasons why I want to separate the concept from its implementation. Because when you look at a model and it doesn't agree with the observations, you really need, you could be looking at one or the other. You could be looking at a bad numerical solution, or you could be looking at a missing process. And you really need to learn to understand the difference. In this case, we were looking at bad numerical transport. People were using spherical transport schemes, or they were using numerical schemes with filling. Either one of those, because the constituents have different gradients, either one of them is guaranteed to fail, and you do not produce correlated constituents. And we were puzzled about this for a long time because the data were clear and the models just didn't do it. For a while, we were hoping it was only in the lower stratosphere, but the satellites tell you, no, it's not, it's global, and these different colors are different pressure levels, and show you that these long-lived species maintain these correlations to very high levels in the stratosphere. And it's everywhere, it's global, it's not just high latitude. The upshot of all of this was to place physical constraints on numerical transport and to learn how to do a better transport scheme. And we switched from spherical transport or center differences to what are called upwind flux-limited shock capturing schemes. That's a lot of words, but what it really means is you look to see where the wind is coming from, you look behind you, and then you figure out what's coming in your direction. And it's flux limited because you can't let it go too far in one time step because you're on a finite grid. So from a physical point of view, it makes a lot of sense to do it this way. You can maintain sharp gradients, and you maintain constituent correlations. And when we did a simulation and compared with Tom's data, we found that if we sat at one point in our simulation, this is just a seasonal simulation with very parameterized chemistry, and you're looking at the data here in a dark line and the model in a light line, you find that you could really simulate this day-to-day variability. And when we created this plot, we were so excited. I can barely explain to you how excited we were when we made this plot. And we managed to show it in like 11 different foreign countries and on 3 continents because we were really excited about it. Well, on reflection, okay, why did we get this? We got this because we had redone our transport. You couldn't do this if you hadn't gone through this step of understanding what was happening with the numerical transport. But on reflection, once you had made that big step, as long as you had halfway reasonable chemistry, you're going to get this result because what you're looking at is the movement of the polar vortex. And so this result went from being one that we thought was really exciting with strong scientific implications to being one that, well, you really need to get this. If you can't get this, you're going to need to go back and redo your numerical transport because you've obviously made a mistake. So that's kind of the life of the modeler. It's like you have a good result 1 minute, and then 10 minutes later, well, you're going like, well, what's the matter with it over here? And also considering it to be now it's a requirement. You know, it used to be a solution. Now it's a result. And within like about 15 minutes, it becomes a requirement. So we're going to make a pause. I just said that part. Even with simple photochemistry, realistic meteorology guarantees that result. But I want you to remember this relationship of the simulated CLO and NO to the observed present and the simulated prediction. This is the kind of thing that can test your conceptual model. And that's the kind of thing that we were spending a lot of time on. The tracer work, whether it's 2D or 3D, is really testing implementation and not the conceptual model. It's testing your numerics, and it's testing the circulation that you're feeding in. So you really need to be able to tell one for the other. By the late 90s, we would say the stratospheric conceptual model is pretty much settled. And we began, I guess, really in the early 2000s, a successful collaboration between the Atmospheric Chemistry and Dynamics branch and the GMAO, where we took our chemistry, first stratospheric chemistry that we had developed in the CTM, and then second, stratosphere and troposphere photochemistry, which I'll describe later, and coupled it up with the general circulation model from the GMAO, which was originally GS4, and now it's GS5. It's an improved version. So when I had come here, as I said before, we were involved with what was called the Stratospheric General Circulation with Chemistry project, where we were going to produce this model in the 1980s, and it took us quite a while to get there. I could point out for the computing, if you're younger, it's very hard to get your mind around this, but in the CTM with specified meteorology, with the full-up computing resources that we have when we first put the model together with full chemistry, we could compute 6 days per day. Okay, so 6 simulated days per day. That means if you wanted to do a year, it took several months, if everything went well and you got the computer the whole time. So now we just compute like gangbusters compared to that. When people are impatient, I just say to them 6 days per day. Yeah. So they know where we came from. So this CCM that we managed to produce in this calculation, CCM is Chemistry Climate Model, makes full use of the satellite data. This is one of the first figures that we produced, and it's one that I don't get tired of showing people. This is what's called the tropical tape recorder. And so what the observations tell us first, this is data here in the middle, is that you have ascent in the tropics and poleward and downward transport mid to high latitudes. That's the Brewer-Dobson circulation description, and we've known about that for a really long time. Stratospheric water vapor varies seasonally with the tropical tropopause temperature. So when it's warmer, you get more water, and when it's colder, you get less. And some other data was showing that horizontal mixing between the tropics and mid-latitudes is minimal. I think you could see some of that originally in the SAGE data and the aerosol data back in the 80s or the early 90s. So the net result of this is that if you take water vapor for a year and average it and compute the anomalies, and you look at the anomalies, you can see the anomalies ascend. So like it's cold here, and then that's going to ascend with time. It's warm here, higher water, and that will ascend with time. And they call this the tape recorder because as air parcels ascend, they're retaining the memory of where they've been. And to have this, you have to have pretty limited mixing between the tropics and mid-latitudes, or you would just wash this kind of signal away. When you simulate this, and you get something that looks this good, it's pretty exciting. It means your tropical temperatures are correct, but it also means your rate of ascent, the outflow from the tropics, and the horizontal mixing are all correct. We were even bold enough to overlay this to show you that our ascent rates, the approximate fall off with height, is as observed. And this has become an important metric for evaluating model performance. One of the questions we had when we originally did this, can we test the coupling between the ozone and the dynamics? And we were looking at a CCM simulation, one in which everything was fully coupled, and comparing that with a simulation that we had done with the CTM without coupling. And what we found in the CCM simulation, when we made the ozone hole, which is down here in the summertime, we had this increase in ozone, and this is below 10 millibars. So this the photochemistry isn't fast enough for this to be caused photochemically. This has to have an element of the transport causing this to happen. And we had a group meeting, and we're looking at this, and we're going, wow, look at that big change. I thought, wow, you ought to be able to see that in the data. And like 20 minutes later, we had this plot of the SBUV data showing us this previously unexamined increase in ozone that comes from the change in the transport that happens because of the ozone hole. So because I like to think this is the advantage of really working at Goddard, because if you work at Goddard, you're really in touch with the people who really have the measurements, you're in touch with the data, and you don't just produce something. There were 2 papers prior to this one that attributed this increase to something completely different and had no data in it at all. But if you worked at Goddard, you would never think of not looking in the data. I think that's the advantage of being here. And the comparison does test whether our coupling makes sense. Now, what's the situation today? We do not have the only chemistry climate model in the world. There are many of them. There's 14 or 18, kind of a large number. But in a basic sense, all of these models have the same underlying conceptual model. And this international group, SPARC, sponsored a coordinated approach to evaluation of these models, which is called CCM-VAL. Many groups participated and submitted their results, first to CCM-VAL and then to the WMO Scientific Assessment of Ozone Depletion. And I say it seems like only yesterday we were doing that, but we're already gearing up for the next assessment. They're a little relentless as well. But you can spend a little time looking at these and wondering what's going on with them. So this is what the models looked like for 5 millibar ozone in the tropics. And this is actually a discouragingly large range of values because, as I said, these models all have the same conceptual model. And so you look at that and you feel a little depressed, at least I did. And even when they normalize and reference everything to the same year, you can see that there's a huge spread in the values, well, the time that you get back to an unperturbed condition. So we have a discouragingly large range of values. Photochemical mechanisms are the same, but the implementation isn't always as good. The GCMs have strengths and weaknesses, and I think it is our responsibility to figure out how to take strengths and weaknesses into account and explain why these projections are different. So we go back to ozone and temperature correlations, where we started with a conceptual model, where the O plus O3 is the most temperature dependent, and O plus NO2 is second, O plus hydrogen reactions third, O plus CLO is the last. So if it's too cold, ozone will be higher, And if chlorine increases, ozone will become less sensitive to the temperature change. So we looked at this first in our model, and you can write ozone as a function of an exponential function of temperature. And that's sort of a weighted sum over the loss processes. And you can calculate that from the annual cycle for ozone every year, and you can compare it to what you derive from observations. And you can also compare it to what you got if the chemistry was constant. Constant chemistry, it wiggles around, but it doesn't change. In the model, if we let chlorine increase, it becomes less sensitive to temperature, and then it becomes more sensitive again. And we put on points for the LIMS data, for UR's MLS, for hurdles and MLS from aura. And you can see that we're tracking the general shape of what the model predicts. So this idea that as chlorine increases, the atmosphere becomes less sensitive to temperature, and then the reverse, which we figured out would happen in 1986 or 7, actually did happen. So can we use this to tell the models apart? And the answer there, that's a rhetorical question. Well, yes, we can. If you look at the spread in ozone from all those models, and you look at the spread in temperature, and then you look at what their sensitive to temperature should be, you see that you explain almost all of that spread in temperature, or all of that spread in ozone, by looking at the different temperatures that the models produce. So the reason that you have that really big spread of values back here is because the models produce temperatures that vary by 10 to 20 degrees different from observations. And it's a deficiency in the radiation. So that's identified in the CCM valve, but it isn't really used. The other thing that you see is that as you increase chlorine, this is just looking at the standard deviation of the ozone produced by the whole range of models as a function of chlorine. So as you increase chlorine, that standard deviation drops. So that temperature-dependent difference that the models compute becomes less important at higher chlorine. So the exciting part about this, the take-home message, is that our conceptual model, that we all are using the same one and that we developed during the 80s and 90s, really works to explain why those models are different, to identify the cause, and to explain that range in predictions. So we don't have to put it out there as if a group of models, as if we don't know what's making them be different, since we do. Now, I'm sure you're wondering, what about the lower atmosphere? Because most of the ozone is in the lower atmosphere. Well, the lower atmosphere, we have similarly, this is the middle latitude southern hemisphere, this is the tropics, and this is the northern hemisphere. We have a similar large range. So how would you go about understanding this? Well, to understand what's happening to produce that range, you have to look at the transport. And the CCM valve transport evaluation was extensive, using some things that we talked about before, for example, the tape recorder, its phase speed and amplitude, and something we haven't talked about, which is what's called fractional release and is related to the mean age. So we don't have a lot of time here, so this is going to be the short form, but the age is the time since you've crossed the tropopause. And you can get a measure of that by using a long-lived gas like SF6, because it's produced in the troposphere and it's increasing, but it doesn't have a loss. So when you look at what the SF6 is in the stratosphere, and then you go back and say, when was it that much in the troposphere, you kind of know what its age was. And then there's been a lot of work to find out that to get things to be really old in the stratosphere, they have to go up. Like if it just comes in, over, and down, it doesn't stay in very long. But if it goes in, it goes wandering around up into the top, it can stay for quite a while. And they have to go up for the CFCs to be photolysed, because you remember the CFCs themselves are protected from photolysis by the ozone layer. So they have to go above it to be photolysed. So if you look at how much of a CFC is missing based on what its age is, you have a really good measure of how the model is doing with respect to how much it sends up and how much it sends over. It's an integrated measure of the circulation. But the impact of this is to tell you how much chlorine there is in the lower atmosphere. And you can see these X's are from aircraft observations. The lines are all from models, and not picking on any model in particular, just noticing that there's a really big range. And so that's telling you that the amount of chlorine that there is that's not tied up in a long-lived reservoir varies tremendously among the models. The amount of chlorine that is not tied up, in a CFC. So once it's been released from a long-lived gas, the chlorine usually is in hydrochloric acid or chlorine nitrate. And you can measure those columns in the lower stratosphere, and we're going to expect that they're different. And then we can compare them to NDAC measurements, because they've been measuring the columns of HCl and chlorine nitrate for a really long time. So this is the range of models, and the black on here is what the measurements are, and you see this discouragingly large range of what the models are. But if you reduce that and only look at the ones that pass the transport evaluation, you're actually matching the data almost perfectly. So given this plot and how big this range is, and how much we know, how we can use the conceptual model to organize our thoughts, the loss cycles involve radicals and they control ozone loss. The radical amounts are controlled by the distribution of their reservoirs. So the amount of CLO that you have depends on chlorine nitrate and HCl and how they're balanced between the two of them. And for you to get a realistic response in your model, you've got to have a response that looks like the atmosphere. We observe, or we note, that the CCMs that have good chemistry and transport, according to all these tracer evaluations, have a similar response. So that's good, but we're not just saying, okay, everybody else off the island. What we're saying here is we can use our conceptual model and we can explain this range of responses. So again, we don't have to put it out there like a black box and go, oh, this is what the models get. And we don't even need to say, some of these models are better than others. But we can say, this model has a weak response because. And I think that's the important step that we need to be taking now with all this data that we have. Now, where are we now? Modern models, modern CCMs also are now including tropospheric chemistry. Tropospheric composition is going to be affected by stratospheric change. Tropospheric pollutant emissions are changing due to regulation and due to industrialization in various parts of the world. And evaluation of these simulations of tropospheric composition is at an early stage. We have fewer global data sets, we have more variability, and it's more difficult to figure out what should be reproduced without the constraint of specific meteorology. You know, what do you think a climate model should actually produce for tropospheric composition? It's a good, hard question. Well, one of the things that people in our group have been making progress on is understanding the ENSO-related variability of ozone. So that's this oscillation in the sea surface temperature that causes the areas where you have the most storms to move based on whether you have El Nino or La Nina. And Jerry Zimke noted, looking at tropospheric column ozone, that if you took the value in the Western Pacific and the Eastern Pacific and you subtracted one from the other, you would get a difference that actually tracked the El Nino difference almost perfectly. So this is just a data result here. So then we looked at our model, which is forced by observed sea surface temperatures. We wondered how it would do. And we produced this incredible plot that had us really happy, doing that scientist dance of joy, just like we had done years before with the TOMS data and the movement of the polar vortex, where our model is this red line here, and the ozone computed in our model really matches the difference between the Western and the Eastern Pacific, as Jerry put out there, and tracks, of course, the Nino 3.4 index. So we were really excited about this. And we still are. We haven't gotten over it. We're using expanded the analysis to include MLS and test data to look at the vertical structure of the response. Now, in this case, what you have to do is regression analysis to determine what's the sensitivity to ozone at a function of height. This is the data here on the top, and this is the model, and this is for one region. And it shows you this ozone sensitivity to ENSO. So it shows you this good physical response that you can really understand. These dark lines here are showing you how the circulation changes in ENSO. And so these ozone changes really make sense with the circulation changes. On reflection, to me, it seems like this could easily turn into one of those results that now is a requirement. You know, all the CCMs must produce this because this is telling you something very basic about the way ozone and the circulation respond in the troposphere. And I think it's actually making that evolution as a result, sort of even as we speak. So questions remain. Does this CCM success or failure in producing this response to ENSO give insight into the simulated future? That's an open question. Will ENSO frequency or character be different in a changing climate? That's another open question. Is there an ENSO impact on the oxidizing capacity of the troposphere? That's a hard question because to get that right, you have to have the storms right, the lightning right, and a lot of other things right besides just their location and the transport difference. And again, that's an open question. To sum up this whole talk, the conclusions, the ground-based aircraft and satellite observations really play complementary roles in developing that conceptual model. And looking back on it, I think the effort was well spent because it's paid off in realistic behavior for complex models, but more importantly, it gives us a framework where we can identify what must be represented correctly in order to make a good prediction and to understand why different models respond differently when you perturb them. And I think that's really the name of the game when you're trying to do a model and a perturbation. You need to understand its response. The frontier and composition element of chemistry climate modeling is evaluating these simulations for tropospheric composition. It requires further development of the conceptual model, and it's going to require more and better data tools and insight. And I think this is the challenge for the next 10, maybe 20 years. And I just want to add one more thing. When years ago, I belonged to AWIS, which is the Association of Women in Science, and they published an interview with Shannon Lucid, who was an astronaut, and her interview was wonderful. She had a big family like I did, and so I identified with her like I had met her. But when they talked to her and they said to her, "What's your biggest accomplishment?" She said, "Well, it's my children." And then she said, "But if you're asking me scientifically, oh, it's this." And she had a list as long as your arm. And I feel that if you asked me, I would say the same thing. It's my kids. But then there's all this stuff too. And I have the idea that in the world, women will have really achieved equality when I ask a fellow that, and he says, "Hey, it's my kids," but scientifically. Yeah. So that's something you can kind of think about. Thank you.
Okay. And by the way, I should say that she's also a tap dancer, so despite being a mother, she also enjoyed dancing. So a few comments and questions, please.
First, it was great, a great talk, and very, very impressive that you brought up 5 children. But since you started with, the times that you grew up in, I grew up in those same times, and one of the things that was really impressed on me was the biggest sort of problems that are coming is overpopulation. So your 5 children.
No, it wasn't my plan to have that many children. I just did.
Okay.
Each one an amazing blessing.
One last comment or question? Okay, yeah, please.
Since I got my PhD in solid state physics, I'd like to know what it was about it that you hated so much.
Pardon me?
That
What
you
do you
didn't
hate
like
so
about
much?
solid state physics.
I don't really know. Probably it was that I was struggling with the commute, the 40 miles, and that I really couldn't be thinking about doing lab work anymore. And a theoretical solid state was just like over the moon as far as I was concerned, and it didn't feel practical at the time. I mean, maybe it is. I don't know enough about it. I mean, I took one class in it, and I was just like, this is not for me. And I moved on to other things. But it's my brother's a fiber optic scientist and had a wonderful career and knows a lot more about all those sorts of things than I do. And I admire my brother and his career, so I have to say it wasn't all bad. Certainly we wouldn't have the satellites that we had today if there hadn't been amazing advances in solid state or computing, you know, or much of anything. So I don't mean to badmouth solid state, it just wasn't for me.
So once again, let's thank Anne Douglas for a good talk.